Hi all, good morning. Is the audio video volume, is everything clear? So let's start now. In this lecture, we will study Euler and Hamilton graph. So there are two type of graph, Euler graph and Hamiltonian graph. So this we will study. Also, we will study graph realization problem. Okay, so these two topics we need to study. Let's start. So the first problem, the first topic is Euler and Hamilton. Euler and Hamilton graphs, basically. Okay, Euler and Hamilton graphs. What are these? What are these graphs? So actually there are two problems. Okay, there are two well-known problems. One problem is Euler problem, another is Hamiltonian problem. And what are these problems and what they are asking? So there are two problems. One is Euler problem. One is Euler problem. Another problem is Hamiltonian problem. Okay, so Hamiltonian problem. And what are these problems? So this problem, this Euler problem, this problem says that can you, like, for example, you have a graph, and in this graph, what you do, like, okay, choose your vertex. That is your, okay, that is your choice. So is there some vertex? Is there some vertex where you can start? So you can start at this vertex, visit every edge exactly once, visit every edge exactly once, and then come back. Visit every edge exactly once, visit every edge exactly once, and come back. Okay, so what this problem says, this problem says that visit every edge exactly once, visit every edge exactly once. Every edge you have to visit, but exactly once, not more than one, not less than one. Okay, you have to visit every edge exactly once. So this is the problem. This is your Euler problem. Euler problem means visit every edge. You have to visit every edge and exactly once, and you have to come back to the same point. Okay, so these are the two conditions. You start at some vertex, and can you visit every edge exactly once and then come back to the same point? This is the Euler problem. And what is the Hamiltonian problem? The Hamiltonian problem is you have a graph G. Okay, in this graph G, you start at some vertex, then visit every vertex exactly once. Then what you do? You visit every vertex exactly once, and then you come back to the same point. So basically, this Hamiltonian says that visit every vertex exactly once, and come back to the same point exactly once, and come back to the same point. So these are the two problems. Are they clear? This problem is saying, can you visit every edge exactly once and come back to the same point? And this problem says, can you visit every vertex exactly once and come back to the same point? So these are the two problems. Like, okay, have you played this game in our childhood? Okay, so in childhood, this game have you played? Like, so what the small children, okay, what they will do? They will create some dots. They will create some dots, and then they will say that, like, okay, for example, they will create a shape. So some shape they will create. Okay, let's assume some shape they are creating, and then after creating this shape, what they will ask? They will ask that put a pen, put your pen, okay, and then don't pick your pen, don't pick your pen, and what you do? You traverse every edge exactly once. Like, for example, I have this pen, okay, I put this pen here. Now what I have to do? I have to basically I have to color this graph. Basically, it's like I have to color this graph, or I can say I have to visit every edge, visit every line exactly once. I cannot go, okay, I cannot pick the pen, and I cannot draw it again. Okay, I cannot draw it again. So it's like I start here, I do this, then let's assume 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 I do this. So you can notice every edge I'm visiting exactly once. I do this, now I do this, I do this, and I do this. Now there is a problem. Yes or no? Can you notice there is a problem? See, I did not pick a pen. I did not pick my pen, and you can notice I'm not visiting any edge more than one time. Every edge I'm trying to visit exactly once. So can you notice there is a problem? Like, okay, I come back here. Now I cannot go out. Yes or no? So this type of game have you played? Can anyone tell me what is this game? So like what problem is this? You cannot pick your pen. You cannot pick your pen, and you have to visit every edge exactly once. You have to visit every edge exactly once. So this is your Euler problem, and you have to come back. Okay, so this is the Euler problem. You can notice. So anyway, so let's see what is the Euler problem. You start at some vertex. You have to come back to this vertex, and you have to visit every edge exactly once. Hamiltonian problem. You have to visit every vertex exactly once. Okay, you start at some vertex, you come back to this vertex. Okay, and you visit every vertex exactly once. If you want to remember, you can remember like this. If you want, you can remember like this. See, Euler means E means edge. Okay, if you have any confusion, then what you can remember like this. Euler means E means edge. Okay, so Euler basically wants to visit every edge exactly once. Okay, and then automatically Hamiltonian means vertex. Is this clear? Like this you can remember if you want to remember. So Euler means visit every edge exactly once. Hamilton means visit every vertex exactly once. And there is one more important point. You have to come back to the same vertex. You have to come back to the same vertex. So this is the idea. So finally I can say that what is this? Okay, so anyway, this is the idea. Now what we will do, we will study both of them one by one. This Euler problem and this Hamiltonian problem, we will study them one by one. Okay, so let's start. Okay, before that, so for Hamiltonian problem, do we have any example? For Hamiltonian problem, do you have a practical example for Hamiltonian problem? Do you have a practical example? What is your practical example for Hamiltonian problem? This is a traveling salesman. Yes, the practical example is traveling salesman problem. Traveling salesman problem. What this means? Traveling salesman. Okay, so this traveling salesman problem. What this problem is? This problem says that you have a salesman. Okay, so let's assume there is a salesman, and like for example, maybe Swiggy. Okay, like for example, maybe this is okay, maybe this is some delivery boy. Okay, so this is some Swiggy delivery boy. Okay, and let's assume this Swiggy delivery boy has to go to these houses. So these are the houses. Okay, these are the locations where he has to go. So he has to go to these houses. Then what he has to decide, what he will do? Tell me one thing. Will he go to same vertex 2 times? Will he go to same location 2 times? He will not go. He will not go to same location 2 times. So okay, so this delivery boy, this is the traveling salesman. He is traveling, and what he will decide? He will decide that can I visit every vertex exactly once? Can I visit every vertex exactly once? And I have to come back to the same point. Of course. Okay. Can I visit every vertex exactly once and come back to the same point? Okay. So this is the idea. This is the Hamilton problem. This traveling salesman. So there is a salesman who is traveling, who is visiting cities. These are the locations, and what he want to do? He want to visit every location exactly once. Every vertex he want to visit exactly once, and he want to come back to the same point. Okay, so this is your traveling salesman problem. This is the example of Hamiltonian problem, and this game is the example of Euler problem. Okay, tell me one thing. If you are not repeating vertex, can edge repeat? Saurabh, without repeating vertex, can edge repeat? If no vertex repeats, then can edge repeat? If no vertex repeats, okay, then it automatically implies no edge also cannot repeat. No edge also repeats. Just think about it. If you want to repeat a edge, then you have to repeat vertex. Yes or no? If you, like for example, this is your edge. If I want to visit this edge again, if I want to repeat this edge, then these two vertices will be repeated. Okay, so no vertex repeat automatically implies no edge repeat. But remember, this is not correct. This is not correct. For example, you can have a graph like this, A, B, C, D. This graph you can have, and here what you can do, here you can go like this. You can visit this vertex. Okay, so what you can do, you can take a graph like this. This type of graph maybe you can take. Okay, so what I'm saying here, you can repeat a age. No, okay, if I don't repeat any age, then can I repeat a vertex? If I don't repeat any age. So for example, like, okay, actually in this example also you can notice, in this example, this age this vertex I'm repeating. Actually in this example also you can notice that this vertex I'm repeating. This vertex, if you notice, this vertex, this vertex, this vertex, just notice this vertex. Notice this vertex. This vertex I'm repeating. Many times this vertex I'm repeating, like, okay, I start here, this green one, I start like this. Okay, so I'm going like this, and then you can notice that I'm repeating this, then I'm going here, then I'm going here, then I'm going here. So okay, without repeating age, I'm repeating vertex. So this is possible. Okay, so anyway, this is the idea. So if you don't repeat any vertex, then no age repeats automatically. Okay, so these two things, no vertex repeat, automatically implies that no age also repeat. But if no age repeat, then vertex may or may not repeat. Okay, let's move on. Now we will study Euler. This Euler problem we will study first. What is this problem? First, okay, what is Euler circuit? You know the definition of circuit? Tell me the definition of circuit. What is that? Circuit is a closed trail. Circuit is what? Circuit is a closed trail. And in a circuit, what is not allowed? In a circuit, age repetition not allowed. Age repetition is not allowed in circuit. In a circuit, yes or no? Age repetition not allowed. This you already know. Okay, this concept we already know, the concept of circuit. For example, if I give you this graph, A, B, C, D. Okay, if I give you this graph, then in this graph I can say this is a circuit A, D, B, C. Okay, like A, D, B, C, then again A, and then D. Okay, then B. Okay, so you can notice this is a okay, so this is actually a trail. This is a trail. This is not a circuit. This is a trail. What is this? This is a trail. This is not a circuit. Okay, because what is happening here? So you are going like this from A to B. You are going from A to D. Then you are going to B. Then you are going to C. Then you are going to A. And then you are going to B. So you can notice this is a trail. In a trail, A's cannot repeat. But this is not a circuit. This is a trail. This is not a circuit. Okay. And what is a circuit? For example, if I want a circuit, then I can have this graph, like, okay, like A, B, C, D, E, F. This type of graph I can take, G, something like this. Okay, in this graph you can notice that what I'm doing. Okay, if I do like this, from A I go to B, then I go to C, then I go to E, then I go to F. Okay, then I go to G, then I go to C, and then I go to D, and then I go to A. This is circuit. Yes or no? This is circuit. No age is repeating. What I'm doing, I'm starting here and I'm going to B, then I'm going to C, then I'm going to E, then I'm going to F, then I'm going to G, then I'm going to C, then I'm going to D, and then I'm going to A. So this is a circuit. Circuit means closed trail. Circuit means closed trail. You start here and you are coming back without repeating edges. Okay, you are not repeating edges. So you start here, and then what you do, without repeating edges, you can come back. You can repeat vertices, like this vertex you are repeating, this vertex you are repeating. So you can repeat vertices, but you cannot repeat edges. This is the definition of circuit. Circuit is a closed trail. Edge repetition is not allowed. Vertex repetition is possible, no problem. Okay, is this clear? Circuit. So what is Euler circuit? Euler circuit means a circuit in which every edge is visited exactly once. Every edge you have to visit, every edge. Okay, you cannot leave any edge. So that is your definition of Euler circuit. Euler circuit means a circuit which is Euler, a circuit which covers every edge exactly once. This is the definition of Euler circuit. And any graph which has Euler circuit, that will be called Euler graph. If your graph has Euler circuit, at least one Euler circuit, if your graph has, then that graph will be called Euler graph. Now let's first understand from where this Euler problem came. What is the beginning of this Euler problem? Okay, so the beginning of this Euler problem, this is basically in a city called Konigsberg. This is, I think, in the Persia. Okay, I think Russia or something. So this is a city, Konigsberg. In this Konigsberg, this type of city is there. Was there, or I don't know, like whether it is still there or not, I don't know. Okay, I don't have information, maybe. Okay, so but anyway, this is the city. In this city, what is there? Like, okay, so there are basically like, okay, this is a land and this is a bridge. Okay, and this is another land and this is a bridge. And you can notice this is a river. Okay, so like this. So basically, total how many land masses are there? How many piece of land you have here? So you can notice total 4. Okay, and total 7 bridges you have. So this is a city. Now actually there was an interesting thing going on at that time. Okay, at that time, almost okay, so there was a thing that is this is actually, you can notice this problem. This problem is actually very old, or almost 1837 around. Okay, so this problem. So what is the problem? So in this city of Konigsberg, there were 7 bridges. So this was the city. And what people used to do, it was said that residents spent their Sundays walking, okay, Sundays walking, trying to find a way to walk about the city so as to cross every bridge. Okay, so this is what they used to do. Cross every bridge exactly once and then return to the starting point. This is what people used to do. Okay, stupid people. So you can notice, because of them, our graph theory started. Because of them, your syllabus got expanded. Okay, so anyway, so you can notice this is what these people used to do. So this was the city. This was the city. And in this city, what they did, they used to walk. They used to walk, okay, and cross every bridge exactly once, cross every bridge exactly once, and return to the starting point. What is this? Tell me, what is this definition? Cross every bridge exactly once and return to the starting point. This is your circuit. This is your Euler circuit. This is the Euler circuit. Okay, so this was the problem. So what this Euler did, let me tell you, this was an open problem. This problem was open because mathematicians for almost 200 years, the mathematicians, they could not derive a theorem. See, mathematicians, like, okay, you can do manually because only 7 bridges are there. Only 7 bridges you have, so you can check manually. But what I'm saying, mathematicians don't want manually. They want some theorem. Like, for example, if there are 1,000 bridges, then what to do? If there are, okay, if there are 20 bridges, 50 bridges, then what to do? So they wanted a theorem. They wanted to prove, like, when it is possible. This is possible or not. Means you start at some vertex, you visit every bridge exactly once, and then you come back to the same point. Is it possible or not? Okay, in which graph it is possible? In this city, is it possible or not? So this was a problem. This was an open problem. So what this Euler did, he converted this city into graph. This city he converted into graph. Okay, this is what Euler did. So like, you can see what this Euler did. This is the city, and this city he converted into graph. So like this he converted. This is your city. So let me call it vertex A. Let me call it vertex B. Let me call it vertex C. Let me call it vertex D. So I can convert this city into a graph. Okay. So A, B, C, D. These are your vertices. And what I can do, so you can notice between A, comma B, there are how many bridges? Between A, comma B, there are 2 bridges. There are 2 bridges between A, comma B. So there are 2 bridges. There are 2 edges between A, comma B. We have 2 edges. Okay. Next, between A, comma C, there is 1 bridge. Between A, comma C, we have 1 bridge. Next, between B, comma D, we have 2 bridges. B, comma D, we have 2 bridges. And next, between D comma C, we have one bridge, and also between B comma C we have one bridge. So you can notice total how many bridges you have. Total 7 bridges you have. So what this Euler did, this is what Euler did. Euler converted this city he converted into a graph, where every vertex is a landmass, and every edge is basically a bridge. Every edge is a bridge. This is what Euler did. So Euler converted the city into this graph. And for this graph, Euler proved something, some very interesting result he proved. So you can notice this problem. If you read this problem, that you need to start, okay, you start at some vertex, that is your choice. You can start here or here, but you start at some vertex, you visit every bridge exactly once, and you come back to the same point. So that is known as Euler circuit problem, or I can say Euler problem, or I can say now you have to find Euler circuit. This is what you have to find. You start at some vertex, you visit every bridge exactly once, and you come back to the same point. You come back again. So that is called Euler circuit. So this is what Euler did. And Euler observed one thing. What he found? He found that existence of such circuit depend on the degree. Basically, he found this. He found a very nice result, and he found that in your graph, this type of circuit is there or not. That will depend on the degree. That will depend on the degree of odd degree vertices. That will depend on number of odd degree vertices. First, you tell me, is this problem clear to everyone? This 7 bridges of Konigsberg. Okay, so now you can notice. Let's take example. For example, if I give you this graph A, B, C, do we have a circuit in this? In this, do we have Euler circuit? Euler circuit exists. Tell me, does Euler circuit exist? Euler circuit. In short, we will call it EC. Does it exist? Okay, so here in this graph, EC does not exist. You can check, EC does not exist. For example, if I start here, then I can visit this edge, I can visit this edge, but I cannot come back. I cannot come back to A, because I cannot visit edge more than one time. So here in this circuit, in this graph, Euler circuit does not exist. What about this graph? A, B, C. In this graph, Euler circuit exists. You can start here, you can go like this, and you can come back. Okay, so here the Euler circuit exists. Okay, what about this graph? A, B, C, D. What about this graph? Check it. Can you check it? Try. Okay, can you try? Just try this. For this graph, Euler circuit exists or not? Euler circuit exists or not? For example, if I start here and let me go like this, let me go like this, let me go like this, let me go like this. Okay, so this will not work. This will not work. Okay, let me start here. Let me start here. Let me go like this. 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 Now I cannot go to B. Can you notice? I cannot go to B. Okay, are you getting this point? Let me start here. Let me start here. Okay, so let me start here. Let me go like this. Then let me go like this. 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 Now I cannot come back to C. So whatever you do, A, B, C, D will work. A, B, C, D. How are you visiting every edge exactly once? How are you visiting every edge exactly once? You have to visit every edge exactly once, and you have to come back to the same point. You have to visit every edge exactly once. Every edge you have to visit, and you have to come back to the same point. Please understand the definition. Please understand the definition. Euler circuit means what? Euler circuit means what? There are two things. Okay, there are two things. Visit every edge exactly once. Every. Let me write it in capital. Visit every edge exactly once. Visit every edge exactly once. Not less than one, not more than one. And come back to the same point. And come back to same and come back to starting point. This is the definition. Read this definition. Is this clear? So, okay, in this Euler circuit does not exist. Whatever you do, Euler circuit does not exist in this graph. So now there is a problem. What is the problem? In which graph Euler circuit exists? Yes or no? This is a nice problem, that in which graph Euler circuit exists. Euler circuit means you start at some vertex. Euler circuit, what it means? It means you start at some vertex. That is your choice. You start at any vertex, visit every edge exactly once, and come back to the starting point. This is called Euler circuit. Now you can notice some graph have Euler circuit, like this graph has Euler circuit. This graph does not have Euler circuit. And what about this graph? Like, for example, if I give you this graph, A, B, C, D, E, F, G, H. Okay, so tell me, this graph, Euler circuit exists or not? In this graph G, Euler circuit exists? Euler circuit, does it exist for this graph? Yes, for this graph, Euler circuit exists. Yes, there exists, because what you can do? Very simple. You can start here, A. You can start at A. You can start at A. You can go to C. You can go to D. You can go to B. You can go to G, and so on. Every edge I am visiting exactly once, and I can come back. So for this graph, Euler circuit exists. Euler circuit exists. You can start here. Then you can go to C. Then you can go to D. Then you can go to B. Then you can go to G, F, E, then B, and then A. Okay, this is your Euler circuit. Very simple. And tell me now tell me, does Euler circuit exist? Now you can check. Okay, Euler circuit does not exist now. In this graph, Euler circuit does not exist. So there is an interesting problem. What is that? What is the interesting problem? This is the interesting problem. That which graph have Euler circuit? This is the interesting problem. Which graph have Euler circuit? How to decide? So first, let's see the definition of Euler graph. Before, okay, so what is Euler circuit? This you already know. Euler circuit means, okay, Euler circuit is a, and let me tell you one more thing, because this might confuse you sometimes. Let me tell you that all these words have the same meaning. Euler circuit. So you can call it Euler circuit. You can also call it Euler tour. Okay. You can also call it Euler circle. Some people call it Euler cycle. Remember, actually, it is not a cycle. If you notice, it is not a cycle, right? Yes or no? In a cycle, you cannot repeat edges. In a cycle, you cannot repeat edges in a cycle. So like this type of thing is cycle, and this type of thing is circuit. This is your cycle, this is your circuit. But because of this word, Euler, because of this Euler word, all these things are same. Is this clear to everyone? All these things are same. All these words are same. Because of this word Euler, whenever you see this word Euler, it automatically means that we are talking about Euler circuit. We are talking about every edge we have to visit exactly once, and vertex you can repeat. You cannot repeat edges, but you can repeat vertices. So remember, whenever you see this word Euler, anyway, these four things are same. So don't say that Euler cycle, sir, how can it be cycle? In a cycle, we do not repeat edges. Don't say that, because Euler cycle, this Euler word is important. Euler circuit, Euler tour, Euler circle, Euler cycle, all these words are same. Now let's see the definition. The definition is this: Euler circuit is a circuit in which you have to visit every edge exactly once, and you have to come back to the same point. You have to come back to the same point. So that is covered by this cycle or circuit. So you can, okay, some people call it cycle, some people call it circuit, but the idea is definition is same. Okay, like you can write circuit also, there is no problem. This is actually better. But what I'm saying, that Euler circuit, Euler cycle, all these things are same because of this Euler word, because of this statement. So Euler circuit means it is a circuit in which, in a connected graph, your graph must be connected, right? Your graph must be connected, because if you have disconnected graph, can you have Euler circuit? Tell me, if your graph is disconnected, like if your graph is like this, A, B, C, D, E, F, G. Now you can notice in this graph G, this is your graph G. Now in this graph, you cannot start, like you cannot start here and you can come back by visiting all the edges. Okay, so again in this graph, Euler circuit does not exist. So this graph is also not Euler graph. I can say this is not Euler graph. This is also not Euler graph because you cannot visit all the edges exactly once and come back to the same point. You cannot do that. Okay, so this is the idea. So I can say this is the definition. Euler circuit is a circuit in which every edge is visited exactly once. Okay, and because of this word, you have to come back to the same point. You have to come back to the same point. So you can notice some graphs have Euler circuit, others do not. And what is a Euler graph? Euler graph is a connected graph which has Euler circuit. This is the definition. Okay. So this is a simple definition. So Euler circuit is okay. All these are different. Like all these are same definitions. All these are same. So this is Euler circuit means a circular trail, means a circuit which visits every edge exactly once, and every graph which has Euler circuit, that is Euler graph. This is the definition. Now this is the interesting point. Which graph are Euler? Like which graph have Euler circuit? This is an interesting question. And for this question, I want to ask you, tell me one thing. Is it possible that you can have odd degree vertex? Okay, let's ask. Before I ask this, let me ask this question. Let me ask this question. Is it possible? Okay, is it possible that you can have odd degree vertex? Let's check out. Is it possible that you can have odd degree vertex? You can have odd degree vertex. Odd degree vertex in Euler graph. In Euler graph means if your graph is Euler, if I assume your graph is Euler, then can you have, is it possible that you can have odd degree vertex? Can you have odd degree vertex? And the answer is no. And the answer is no. The answer is no. See, very simple logic. Logic is very simple. Like let me take a small graph. Like for example, let me take n equal to 2. Okay, in this you have odd degree vertex. Do we have Euler circuit? Tell me, is this like do we have Euler circuit here? Do we have Euler circuit? No. Okay, so this is not Euler graph. I can say this is not Euler graph. Now let's assume that you have, let's assume that your number of vertices is greater than equal to 3. Let's assume. So you can notice with the two vertices, you do not have Euler graph. With the two vertices, you do not have Euler graph. With the two vertices, you do not have Euler graph. Now let's see. Let's assume that your number of vertices is greater than equal to 3. Now, can you have odd degree vertex? Let's check it out. Just think about it. Let's assume there is an odd degree vertex. Assume this is odd degree vertex. Assume, okay, let's assume V is odd degree vertex. Then what will happen if this is odd degree vertex? Just think about it. If this is odd degree vertex, then what will happen? Then it means this has odd number of edges. It means this has odd number of edges. So your V, this is your odd degree vertex. So it means that this is your, and the graph can be something. Okay, I'm only focusing on V. Your graph can be anything. Your graph is like this. Now you notice one thing, very interesting thing. Okay, you need to visit all these edges, yes or no? All these edges you need to visit exactly once. So let's visit this ways. Let's assume I visit this edge. Now from somewhere I am coming and I am coming here. Okay, if I am coming here, then I have to go out also because I have to visit every edge exactly once. Now let's assume after some time I come back from this edge. Then I have to go out also because I have to visit every edge. I have to go out also. After some time, I come back. Now there is a problem. What is the problem? Now I cannot go out. Let's assume this is the source. Now I cannot go out. Yes or no? Is this clear? So very simple. Is this logic clear to everyone? This idea. You cannot have odd degree vertex because notice that you want to visit every edge exactly once. And because you want to visit every edge exactly once, so whatever vertex you take and you want to visit every edge, like let's assume this is the source vertex, okay, and you want to visit every edge exactly once, then what should happen? Then if you are going here, then you should come out, because ultimately you want to go back to S. This is your source, so you want to go back to this. So if you are going into V, then you have to come back out of V. Again, if you are going into V, then you have to come back out of V. Again, if you are going into V, then you have to come back out of V. So whatever you do, you need even degree. Yes or no? Whatever you do, you need even degree. Is this clear? So this must be even degree. Must have even degree. So this is the idea. Very simple. So the idea is very simple. This must have even degree, right? Because, okay. Because if you don't have even degree, then there is a problem. And what is the problem? You cannot come back to source vertex. There is a problem. Okay. So very simple idea. Now, this is the theorem we have. So which graph have Euler? And this is decided by number of odd degree vertices. If your graph is Euler, this is the theorem. This is a very nice theorem. A graph is Euler if and only if. This is a if and only if theorem. This is if and only if theorem. So a graph is Euler if and only if it is connected and every vertex has even degree. So very simple. A connected graph is Euler if and only if every vertex has even degree. Each vertex is of even degree. So this is the idea. Is this clear? Is this clear to everyone? So if your graph is Euler graph, then every vertex should have even degree. Let's check. Is this graph Euler graph? Check it. Okay. So what we have is this Euler graph. Let's see. So remember, this is the idea. Very simple. This is the if and only if theorem. If you have Euler graph, if your graph is Euler graph, then it automatically means that, okay, it means every vertex even degree. Each vertex has even degree. Each vertex has even degree. Each vertex has even degree. And you can notice that if each vertex has even degree, then this will be Euler graph. So this is a if and only if theorem. Very simple. Now let's see, is this which graph are Euler? Is this graph Euler? Tell me. Is this graph Euler on your screen? So this vertex has degree 4. See, this vertex has degree 2. This vertex has degree. This vertex has degree how much? This vertex has degree 5. Okay. So you can notice this vertex has degree 5. And because you have some vertex of degree 5, that's it. This is not Euler graph. So finally, I can say not Euler graph. Not Euler graph. Okay, very simple. This is not a Euler graph because you can notice you have at least one odd degree vertex. Because you have odd degree vertex, so this is not Euler graph. This is a Euler graph. You can notice every vertex has even degree. So this is Euler graph. Like this is 4 degree vertex. This is 4 degree vertex. So this is a Euler graph. Next, what about this? Degree is mentioned. Already degree is given to you. So this is also Euler graph. Very simple. All vertices have odd degree, even degree. So this is an Euler graph. Is this concept clear? Which graph is Euler graph? Is this concept clear? So tell me, which is Euler graph? Like which graph is Euler graph? Which is Euler graph? Euler graph means any graph which contains Euler circuit. Euler graph means Euler circuit, and you have Euler circuit if and only if every vertex has a even degree. So tell me about Kn. For example, about K even, another about K odd, another C even, another C odd, another P even, P odd. So tell me, what do you think? Which is Euler? Which graph is Euler graph? Which of them? Euler graph means any graph which has Euler circuit. Any graph which has Euler circuit. And you can notice that Euler circuit means if and only if every vertex has even degree. Every vertex has even degree. In this, every vertex has how much degree? Every vertex has odd degree in this. Okay, so this is not Euler graph. This is not Euler graph. For example, your K4. In this K4, degree of vertex is 3. So this is not correct. This is correct. This is correct. Because if you have, for example, K5, then degree of every vertex is actually 4. So this is correct. What about this? This is also correct. Degree of every vertex is 2. Degree of every vertex is 2. This is also correct. Degree of every vertex is 2. Degree of every vertex is 2. And this is not correct. This is not correct. Because they have, yes or no? Here, every vertex has degree 2. Is this clear to everyone? And what about P even, P odd? So these are not, because you can notice that they have 1 degree vertex. They have odd degree vertex. This corner vertex will have odd degree. This corner vertex has odd degree. Okay, so whatever you do, this corner vertex has odd degree. So these are not Euler. Next, what about Qn? What about Qn? What about Wn? What about these graphs? Qn, Wn, Km, n. And what about D regular? What about these graphs? Yes, P1 is Euler. Yes, P1 is Euler. So here I can say this one vertex, this P1 is Euler. This one vertex, this is Euler graph. This is trivially Euler graph. This is a trivial Euler graph. You can notice this is connected and degree is 0. You can notice every vertex has degree even. Every vertex has even degree. So if you notice this is degree is 0. So this is a Euler graph. Okay, there is no problem here. This is Euler graph. But apart from, okay, Pn, okay, where n is greater than equal to 2, where n is greater than equal to 2, this is not Euler graph. This graph is not Euler graph. Now let's see this question. This is a nice question. Okay, when Qn will be Euler graph? Tell me about Qn. When it will be Euler graph? When it will be Euler graph? Q1 is Euler graph. Q1 is Euler graph. Okay, sorry, Q0. Q0 is Euler graph. Q0 is Euler graph. Q1 is not Euler graph. Q1 is not Euler graph. What about others? What about others? Are they Euler graph? What about others? In Qn, what is degree of every vertex? Tell me. In this, what is the degree of every vertex? Degree of every vertex is n. So you can very easily see that Q2 will be Euler graph. Q2 will be Euler graph. And Q3 will not be Euler graph. This Q3, this will not be Euler graph. This is your Q3, and you can notice this is not Euler graph. So this Qn is, I can say this Qn is Euler graph if and only if, what can I say? This Qn is Euler graph if and only if So Qn is Euler graph, if and only if n is even, because every vertex has degree n in this Qn. You can notice. Okay, so that is the reason Qn is Euler graph if and only if n is even. Let's see about Wn. What about Wn? What do you think? Wn. In Wn, you can notice Wn is never, okay, Wn, this is not Euler graph. This is not Euler graph. What is the reason? This is not Euler graph because the outer cycle, if you notice, this outer cycle, if you notice, every vertex has how much degree? 3. In this outer cycle, every vertex has degree 3. Every vertex has degree 3. Every vertex has degree 3. Is this clear? So this Wn is not a Euler graph. Next, what about Kmn? This Wn is not a Euler graph for all n. Whatever n you take, this is not a Euler graph. What about Kmn? Km, n. What about this? This is your complete bipartite graph. In this, what is the degree? Just tell me this point. Like, okay, here you have m vertices, here you have n vertices. Then what is the degree of every vertex? Like, what is the degree? What is the degree here? That will be n. And what is the degree of this vertex? Degree of this vertex, that will be, degree of this vertex will be m. So finally, I can say this Kmn is Euler graph if and only if what? If and only if both m, n are even. Both m, n are even. They both must be even. Because you can notice that every vertex here has degree n, every vertex here has degree n. So this Kmn is Euler graph if and only if both of them are even. And what about d-regular graph? What about d-regular graph? What about this? It must be connected. Remember, it must be connected and d should be even. It must be connected and d should be even. Is this clear? It should be connected because remember, this is also d-regular. Like this is also 2 regular. This graph is also 2 regular, but we don't have Euler graph. This is not a Euler graph. So it should be connected. You can notice this is 2 regular. This graph is 2 regular. Every vertex has degree 2, 2. So this graph is actually 2 regular. So d-regular graph is Euler. D-regular graph, I can say, is Euler graph if and only if it is connected and every, okay, d should be even. Very simple. All these concepts, are they clear? Very simple concepts. Now the next concept is Euler path. Some people call it Euler path. Some people call it Euler trail. Some people call it Euler walk. Again, let me tell you, all these words are same. Again, remember, all these words are actually same because of this Euler. Okay, what is this? Euler path, Euler trail, and Euler walk. Whatever, basically, all these words are same because of this Euler. Now let's see what is this. Actually, there is an ambiguity also here. There is ambiguity also because so far whatever we have seen, okay, so far, like the definition of Euler graph, the definition of Euler graph, the definition of Euler circuit, and the theorem that we have seen, all these things are universal. There is no ambiguity so far. Okay, the definition of Euler circuit we know. You start, you visit every edge exactly once, and you come back to the same vertex. You come back to the starting vertex. That is your Euler circuit definition, and that is fixed. That is universal. Next, Euler graph. Euler graph means a graph which has Euler circuit. And this theorem, a graph is Euler graph if and only if every vertex has even degree. A graph has Euler circuit if and only if every vertex has even degree. So these three things are universal. But these things that, okay, this Euler path, this is ambiguity, means this is author dependent. So let me tell you what is the idea. So there are two type of authors. There are two type of authors. So, okay, like I can say author 1 and author 2. And both type of authors you can find on internet. Okay, different books if you study, then both type of authors you will find. So author one, what he says, author one says that Euler path is basically Euler path or Euler trail, both are same things, there is no difference. So what this author says, this says Euler path or trail, it simply means that it simply visits every, okay, simply visit every word, every edge exactly once, visits every edge exactly once, every edge exactly once, every edge exactly once. Starting ending point can be same or different. Remember, starting ending point can be same or different. This is the only thing we want, that visit every edge exactly once. Starting ending point can be same or different. I can say starting ending point can be same or different. Starting ending point vertex can be same or different, can be same or different. So this is author one. And what is author two? Author two is same. Author two is same. The same thing author two has. Author two has same thing. But the point is starting ending vertex must be different. Starting ending vertex must be different. Only this is the difference. Starting vertex is not same as ending vertex. This is the only difference. So there are two type of author. Okay. Euler path or Euler trail. It simply means that visit every edge exactly once. Okay. And now there are two type of author. Author one says that starting ending point, they can be same or different. And this says that starting and ending point should be different. This is the definition of Euler path or trail. Euler circuit we have already seen. There is no problem there. But we have problem when you have Euler path or trail. Here you have a problem. Is this clear? Tell me. There are two type of author. For example, I can say, let me take this graph. A, B, C, D. Okay. So there are two type of author. According to author one, according to author one, according to author one and according to author two, what will happen? According to author one, author two. According to author one, what will happen? You have Euler. Of course, you have Euler circuit. You have Euler circuit. Euler circuit you have. Euler path also you have. Okay, this is your Euler path also. Is this clear? According to author one, because author one says that Euler, okay, author one says that Euler path means visit every edge exactly once. Can you visit every edge exactly once? Yes. Can you visit every edge exactly once? Yes. Starting ending point can be same or different. According to author two, of course you have Euler circuit, but there is no Euler path. But there is no Euler path. Is this clear? Now let's see the another graph. Let's see another graph. Let's see this graph. Now in this graph, there is no Euler circuit. You can notice in this graph, there is no Euler circuit. Is this clear? Abhipsa, I am taking example. In this graph, there is no Euler circuit. You can check because this vertex at degree 3, this vertex at degree 3. So there is no Euler circuit. But you can notice that according to author 1, there is Euler path. And according to author 2 also, there is Euler path. So let me just give you the definition. Let me give you the definition. So what is Euler circuit? Please note this Euler circuit. Please note Euler circuit. Euler circuit is fixed. Euler circuit definition we have already seen. What is Euler circuit? Euler circuit means you start and you visit every edge exactly once and you come back. And you come back. You start, you visit every edge exactly once and you come back. You come back. You come back. This is the Euler circuit. What is Euler path? What is Euler path? Euler path means you start, visit every edge exactly once. Visit every edge exactly once. Visit every edge exactly once. But you can go to some other vertex also. You can end at some other vertex also. For example, let's take example. Like, okay, let me give you this graph. A, B, C, D. Let's consider this graph. Do we have Euler circuit? Tell me. Do we have Euler circuit? See, this vertex at degree 3. This vertex at degree 3. So there is no Euler circuit. There is no Euler circuit because this vertex has degree 3. There is no Euler circuit. Okay, so here we don't have problem. There is no Euler circuit implies not Euler graph. This is not a Euler graph. But you can notice, if I ask you to visit every edge exactly once, do we have Euler path? Euler path or Euler trail? Do we have this? Yes, we have this. What you can do, you can start at A, you can go to B, you can go to D, you can go to C, you can go to C. Then what you can do, you can go to again A, then D. Okay, so what you can do, A to B, B to D, sorry, okay, so sorry, let's take this graph. Let's take this graph. Okay, only this graph let's take. So you can, what you can do in this graph, what you can do, you can go from A. From A you can go to B, from there you can go to D, there you can go to C, and there you can go, okay, so like this, A, B, D, C, then A, and then D. So now you can notice this is Euler path. Every edge is visited exactly once. So every path, okay, Euler path visits every edge exactly once. Every edge exactly once. Okay, but starting and ending point, they can be different. They can be different. This is the Euler path. Is this clear? Please tell me. Euler circuit, Euler path. This difference is clear. You have to visit every edge exactly once. Here also, here also. Visit every edge exactly once. Visit every edge exactly once. But here you should come back to the same point. You should come back to the starting point. And here there is no restriction. There is no restriction. Here there is no restriction. You can start and you can come back to the same point or different point. So there is no restriction. Both are correct. Okay, so here you have a restriction and here there is no restriction. So Euler path simply says that just visit every edge exactly once. Don't worry about this restriction. Don't worry about this starting and ending restriction. Okay, is this clear to everyone? So what I'm saying, there is small ambiguity in this. What is the ambiguity in this Euler path? There are two authors. One author says that you can, okay, starting and ending point can be same. One author says that in Euler path, starting and ending vertex can be same. And this author too says that, starting and ending cannot be same. This is the only difference. So you can notice this graph. For this graph, author 1 says that you have Euler path. Author 1 says that you have Euler path. Okay, author 1 says you have Euler path. But author 2 says that you don't have Euler path. You don't have Euler path because starting and ending vertex cannot be same. Please tell me, is this point clear? In this graph, according to both authors, you have Euler path. There is a Euler path according to both authors. Whatever author you take, there is a Euler path. You don't have to worry about it. No one will ask you this Euler path. Okay, in the GATE exam, they will only ask you Euler graph. And Euler graph is defined for Euler circuit. So this Euler path is not important. Okay, the only important thing is Euler graph. This Euler graph is important thing. This is important. Euler graph simply means Euler circuit. If you have Euler circuit, and that simply means each vertex even degree. That simply means each vertex even degree. This is the idea. And only this is important. Only these things are important. Euler circuit, Euler graph. Only this is important. This Euler path, this is not important. You don't have to worry about it. Euler path, this is not important. And okay. And by the way, okay, basically there are two type of author, but we will follow this author number 1. We will follow author number 1. Okay, so like one of them you want to follow, then my suggestion is follow author number 1. The reason is because we follow author number 1 in the ISC. Okay, that is the only reason. Author number 1 is followed in IISc graph theory course. Okay, that is also followed in standard this Stanford University. Okay, so that is the reason I am following author number 1. So anyway, this Euler path, this is not important, but what we will follow this. So this is what we will follow now. For Euler path, Euler path simply means that, just forget about this. Forget about this. This is what you take. Please take this. What is Euler path? Euler path means visit every edge exactly once. That's it. Visit every edge exactly once. That's it. Visit every edge exactly once. Okay, so you can visit every edge exactly once. Like you can do this also. This is also fine. And you can do this also. This is also fine. This is also fine. Both are fine. Is this clear? Forget about the ambiguity. I told you about the ambiguity because I know someone will come to me and then they will tell me, sir, in that book, this is written. See, I told you about ambiguity. This is the only reason. This is the only reason. So that you don't come to me and then say, sir, in that book, this is written. On Wikipedia, this is written. In that coaching, this is written. Okay, so don't come to me for this ambiguity. Okay, because I told you there are two type of authors. Anyway, forget about this ambiguity. Forget about this ambiguity. Finally, this is what we will follow. This is what we will follow. Okay, just visit. Euler path means visit every edge exactly once. Starting and ending point can be same or different. Starting and ending point, they can be same or different. They can be same or different. Starting and ending point. This is the idea. This is the definition that we will use. Actually, you can notice this is your author too. As I told you, this is your author too. This is Glimardi. So this Glimardi, he says that you can basically I can say that it should be open, like first and second last vertices, that should be open. Grimaldi, yes, Grimaldi. Okay, thank you. So Grimaldi, yes. So this is the author, Grimaldi. Okay. Anyway, so this is your author too, but we will not follow this. We will not follow this. What is the reason we will not follow this? Because majority of authors, also ISC, majority of authors, they follow this. So you can notice every you can notice this is your author 1. And this is what we will follow. So according to these, every Euler trail, okay, all these are author 1. This is also author 1. All these are author 1 definitions. All these are different definitions. Okay, all these are author 1 definitions. So that is the reason I am following this definition. So okay, let me remove the ambiguity. Please forget about the ambiguity. Forget about the ambiguity. Euler path means, okay, just visit every edge exactly once. Just visit every edge exactly once. This is also fine. And this is also fine. Visit every edge exactly once. This is also fine. This is also fine. This is what we will follow. Forget about everything else. Is this clear to everyone? So according to this, can I say every Euler circuit is Euler path? Can I say every Euler circuit is Euler path? Can I say every Euler circuit is a Euler path? Tell me. Can I say every Euler circuit is Euler path? Yes. Okay. Yes. Is this clear? So forget about that, Karthik. Karthik, forget about that ambiguity. That ambiguity I told you only because I don't want you to come to me and say that, okay, sir, watch this. Don't say that. So that is the reason I told you. Now, forget about that. And this is what we will follow. Euler path. Okay. So I can say every Euler circuit is also Euler path. In this Euler circuit, the starting and ending vertex must be same in this. And in this Euler path, you can have either you can have this type of thing, either you can have this type of thing, or you can have this type of thing. So this is the idea. So I can say that Euler circuit is Euler path. Now let's see one more thing. When can I say a graph has Euler path? When can I say? When can I say a graph has Euler path? So this is the theorem that we have. A Euler path exists if and only if a Euler path exists if and only if there are at most two vertices of odd degree. Either there is no odd degree vertex or exactly two vertices of odd degree. This is the idea. Okay. So you can notice Euler circuit exists if and only if. What is the definition? Euler circuit exists if and only if each vertex even degree. Each vertex has even degree. This is the definition of Euler circuit. You know, Euler circuit exists if and only if each vertex has even degree. Every vertex should have even degree. And when can you say Euler path exists? So you know that Euler path exists if and only if at most two vertices have odd degree. At most two vertices have odd degree. At most two vertices have odd degree. Have odd degree. Tell me one thing. I am saying at most two vertices have odd degree. Is it possible that only one vertex have odd degree? Is it possible? Tell me. I am saying at most two vertices of odd degree. Is it possible that only one vertex have odd degree? Is it possible? Only one vertex have odd degree? That is not possible. In every graph, we have even number of odd degree vertices. We have even number of odd degree vertices. You cannot have one odd degree vertex. You cannot have that. In every graph, number of odd degree vertices is even. That we already know. That is the basic concept. So you can notice this is the reason. At most two vertices of odd degree, or I can say either there is no odd degree vertex or exactly two odd degree vertex. And you can notice Euler circle or Euler circuit exists if and only if every vertex has even degree or no vertex has odd degree. So this is the idea. Is this clear? Let's move on. So tell me here in this you can notice every vertex has even degree in this vertex in this graph. So this has degree 4, this has degree 4, this has degree 4, this has degree 4, this has degree, this has degree 4, this has degree 4. So here you have a circuit, Euler circuit you have. And in this graph you can notice that this is degree 4, but this is degree 3. If you notice, this is degree 3, this is degree 3, this is degree 4, this is degree 4, and this is degree 6. So you can notice, okay, two vertices you have odd degree, two odd degree vertices you have. So you have Euler path. At most two vertices of odd degree. In this graph, what happens? This is degree 4, this is degree 3, this is degree 3, this is degree 3, this is degree 3. So there is no Euler circuit, there is no Euler path. Okay, because we have more than two vertices of odd degree. So that is the reason there is no Euler circuit, there is no Euler path. Please let me know, did you understand this? So, okay, this is the conclusion. If you want, the conclusion is very simple. Euler graph is same as Euler circuit. Euler graph means a graph which contains Euler circuit. And that happens when every vertex have even degree. If and only if every vertex have even degree. Euler path exists. Euler path exists if and only if at most two vertices of odd degree. Is this clear? Is this clear to everyone? Now let's see Euler circuit for directed graphs. In directed graph, when can you say Euler circuit? And this is actually very simple. In a directed graph, again the same logic you will apply. Tell me, if you have a directed graph, the same logic you apply. Your graph is directed. What do you think? What will be the condition? You have some vertex you have. Let's assume this is your source vertex. And let's assume this is your vertex. Then in a directed graph, what should happen? If you enter, you should come out. Yes or no? If you enter, you should come out. Because you want to visit every edge exactly once. You want to visit every edge exactly once and you come back to S. Euler circuit means okay, what you do? You visit every edge exactly once and you come back to S. So if I enter, then I have to come out. After some time, if I again enter, then I again have to come out. Yes or no? After some time, if I again enter, then I have to come out. I have to come out. Yes or no? So what is the logic? Tell me, in directed graph, when can I say Euler circuit exists? In directed graph. In directed graph, Euler circuit exists. Euler circuit exists if and only if for every vertex in degree is equal to out degree. Very simple. For every vertex in degree, incoming is same as outgoing. Okay, so for every vertex in degree is same as out degree. For every vertex in degree is equal to out degree. This is the simple definition. Very simple. For every vertex, this should happen. Euler circuit exists if and only if every vertex has in degree and out degree must be same. Now, when can I say Euler path exists? When can I say Euler path exists in a directed graph? For Euler path. Now, okay, for Euler path, actually you can notice that the source, for source what will happen and for destination what will happen? Tell me this point. See, for the remaining vertices, this will happen. For the remaining vertices, if you enter, you should go out. If you enter, you should go out. But for source, what will happen? For source, what will happen? For source, out degree will be one more than in degree. Yes or no? Like for example, for source, this will happen. Okay, like if you enter into source, then you have to come out of the source. If you enter into the source, then you have to come out of the source. Means out degree should be one more than in degree. And for destination, what should happen? For destination, this should happen. That if you go out, you should come back. But for the destination, in degree should be one more than out degree. So this is the idea. So the idea is very simple that Euler path exists. When can I say Euler path exists? Euler path exists if and only if for every vertex in degree equal to out degree except source and destination. Except source and final vertex. For source, what should happen? For source, you can notice out degree should be one more than in degree. Out degree should be one more than in degree. And for final vertex, in degree should be one more than out degree. This is the idea. Tell me, is this clear? Very simple. For directed graph, Euler circuit for directed graph. So the idea is very same idea. Okay, you have some vertex, then incoming should be same as outgoing. So Euler circuit exists if and only if incoming is same as outgoing for every vertex. But Euler path means this source. For this source, I can say that out degree is equal to in degree plus 1. And for this destination, in degree is equal to out degree plus 1. So very simple point. This is for directed graphs. This theorem is for directed graphs. So you can notice in a directed graph, Euler circuit exists if and only if it is connected. Also, in degree is same as out degree. In degree should be same as out degree. Okay, so that is the idea. Is this clear? Let me know. The next concept, let's take a break. After the break, we will study Hamiltonian cycle and Hamiltonian graph. What is this? This we will study after the break. So let's take a small break. 5 minutes. Hi everyone, let's start. Saurabh is asking a doubt. If a directed graph has Euler circuit, then by definition it won't have Euler path. Again, Saurabh, the same ambiguity here also. Okay, some people they consider Euler circuit also as a Euler path. Okay, so the same thing, the same ambiguity. You don't have to worry about Euler path. This is what I am saying. This Euler path, you don't have to worry. Hamiltonian path, don't have to worry. The only important thing is Hamiltonian graph. The only important thing is Euler graph. Euler graph means Euler circuit. Similarly, Hamiltonian graph means Hamiltonian cycle. Okay, so this is what we have to study. Don't worry about the other thing. So let's see, what is this Hamiltonian cycle? I told you this means every vertex we have to visit exactly once and we have to come back to the same point. So this is the definition of Hamiltonian cycle. Remember, Hamiltonian cycle is actually a cycle and you can also call it circuit. So Hamiltonian, either you can call it Hamiltonian cycle or you can call it Hamiltonian circuit or you can call it Hamiltonian tour or you can call it Hamiltonian circle, whatever, like whatever you want, you can call it. All these things are same. You can call it because of this word Hamiltonian. And this word, what this word means? This word means visit every vertex exactly once. Visit every vertex. Visit every vertex exactly once. This is the definition. This word means visit every vertex exactly once. Okay, and come back to the starting point. And come back to starting point. And come back to starting point. This is the definition. Is this clear? Very simple definition. So you have to visit every vertex exactly once. This is what you have to do. Visit every vertex exactly once. So this is the definition of Euler circuit. And only this will be important. Again, the same ambiguity here also. There are two types of author. Okay, Hamiltonian path. For Hamiltonian path, again, there are two types of author. So some, they do not, some author, they say that Hamiltonian circuit is also Hamiltonian path. And some say that Hamiltonian circuit is not Hamiltonian path. So what is important for us? The only thing important is only this thing is important. Only this thing is important for us. And when can you say graph is Hamiltonian? When can I say graph is Hamiltonian? A graph is Hamiltonian. When can I say a graph is Hamiltonian? If and only if there exists a Hamiltonian cycle. There exists a Hamiltonian cycle. Okay, so this is the definition. Means Hamiltonian graph, that simply means Hamiltonian cycle. Okay, Hamiltonian cycle should exist if your graph is Hamiltonian graph. Okay, so this is the definition. For example, here, tell me, do we have Hamiltonian graph here? Is this Hamiltonian graph? This graph, is this Hamiltonian graph? Do we have Hamiltonian circuit here? Yes, you have Hamiltonian circuit. Okay, you can notice, you can come back. You can go and you can come back. You don't have to visit every edge. Remember, you don't have to visit every edge. You can just do like this. That's it. You have to visit every vertex, you have to visit and you have to come back. So this graph has Hamiltonian circuit. So this is your Hamiltonian graph. This is the Hamiltonian graph. What about this graph? This graph is not Hamiltonian graph. You can notice this is not Hamiltonian graph, but we have Hamiltonian path. We have Hamiltonian path. Okay, in this graph we have Hamiltonian path. This is the Hamiltonian path. Okay, next, in this graph we don't have Hamiltonian path, we don't have Hamiltonian cycle. So this is the idea. So in this we have Hamiltonian circuit. In this we have Hamiltonian path. We have Hamiltonian path. This is your Hamiltonian path. This is the Hamiltonian path. And in this We don't have Hamiltonian path, we don't have Hamiltonian circuit. Okay. Again, remember the same ambiguity here also, Hamiltonian path. How to define this Hamiltonian path? Again, what we will define, how we will define, there are two type of author, the same ambiguity, the same ambiguity here also. The same ambiguity here also. Okay, but what we will follow? So again, there will be same ambiguity. There will be author one. There will be author one. What author one will do? And what author two will do? So there are author one. Author one says that yes, Hamiltonian circuit is Hamiltonian path, is also Hamiltonian path. And author two says that Hamiltonian circuit is not Hamiltonian path. So again, the same type of ambiguity. We will follow this one. This we will follow. Okay, we will follow. So now let me tell you one more thing. Like in the Euler graph, if you want to check Euler graph, there is a very, how much time it will take? Tell me, how much time it will take if you want to check a graph is Euler graph? Checking Euler graph. Checking a graph is Euler. How much time it will take? What do you think? How much time it will take? Time complexity. Time complexity. So checking a graph is Euler. This is very simple. Okay, the time complexity will be order of V. For every vertex, you have to find degree. Yes or no? So checking a graph is Euler. Checking a graph is Euler. That is very simple. You have to find degree of every vertex. Order of V, order of N. And this order of N, this is a very nice complexity. This is very like, okay, this is linear time. This is linear time. And this is a very nice, these algorithms are very nice. They are very nice algorithms. Okay, because they are taking only linear time. So these are nice algorithms and very easy. So this checking a graph is Euler, that is very easy. Okay, all you have to do, just find degree. Find a degree of every vertex. This is what you have to find. Find degree of each vertex. And if every vertex has even degree, then the graph is Euler. And if at least one vertex has odd degree, then the graph is not Euler. Now let's see. Checking a graph is Hamiltonian. How much time it will take? Checking a graph is Hamiltonian. How much time it will take? How much time it will take? So let me tell you that this is a very hard problem. This is a very hard problem. Okay. There is no efficient algorithm. There is no efficient algorithm. This problem is actually, there is something called NP complete. This is a NP hard, or I can say NP complete problem. This is not in your syllabus. What this NP complete problem means? This simply means that it is very hard. It simply means exponential. It simply means exponential time complexity. It will take a lot of time. It will be exponential time complexity. Okay. So for example, let me give you example. Like if I give you 64 vertices graph, if I give you 64 vertices graph, then for Euler, how much time you will need? For Euler, you will need 64 seconds. For Euler, you need 64 seconds. And for this, you need 2 power 64 seconds. Can you check it out? How much is this? Please check it out. Okay, on Google, take your Google, like on Google, you put this value, 2 power 64 second. What is this in years? How many years it is? How many years? How many years you will get? So if you have 64 vertices graph, then Euler will take 64 seconds, and this Hamiltonian, this will take 2 power 64 second, and this is in years. This will be some value in years. Some 1000 years will be there. Okay, can you check how many years are there? In 2 power 64 second, how many years you will get? Can anyone verify? Please tell me. So that is 5 into 10 power 11 years. So this is 5 into 10 power 11 years. Okay, so can you notice? So these are very hard problems. This Hamiltonian, this is a very hard problem. 5 into 10 power 11 years. The whole Kalyug will be gone. You will be gone. Your all the generations will be gone. Their generations will be gone. Kalyug will be gone. Again the Ram will come. Again the Satyug will come. Again that will be gone. Okay, so you can notice, and this algorithm will keep going. This program will keep running. This program will keep running. This program will keep running. So this computer will keep running. Okay, and after these many years, this will give you the output. After these many years, you will get the output. Okay, so you can notice this Hamiltonian problem. This is very complex problem. This is a very complex problem, this Hamiltonian. So we don't have a cute theorem. Okay, we don't have a cute theorem. Like for Euler, we have a very cute theorem. What is that? That okay, for Euler, we have a very cute theorem. All you have to do is just find degree of every vertex. This is the if and only if theorem. You know, this is the if and only if theorem. Very cute theorem we have. So this type of cute theorem we don't have for Hamiltonian. Okay. So there is one way theorem. We don't have if and only if theorem. There is no if and only if theorem. So for Hamiltonian, we don't have any if and only if theorem. Two-way theorem we don't have. Okay, so no two-way theorem. No two-way theorem. We don't have two-way theorems for this. Okay, so this theorem is actually important. This Dirac theorem, from GATE exam point of view, this is not important. This Dirac, okay, Dirac, whatever. Okay, this is not important from GATE exam point of view. But this question has come in the any, like, okay, if you apply some other exams like NET exam, NILIT exam, ISRO exam, these type of stupid exams, if you give, then okay, this will be asked directly. This is important for these exams. GATE will not ask, but for these exams, this theorem is important. And this theorem is a one-way theorem. This says that every graph with n equal to, okay, with at least three vertices, and minimum degree is at least n by 2, then it is Hamiltonian graph. So this Dirac theorem, what this says? This Dirac theorem, what this says? This is a one-way theorem. Remember, this is a one-way theorem. This says that if you have a graph, let's assume you have a graph where number of vertices is greater than equal to 3. Number of vertices is greater than equal to 3, and minimum degree is at least n by 2, then this graph will be Hamiltonian graph. But this is only one way. The reverse direction is not correct. Is it clear? Let me know. So is this clear, everyone? So very simple. This direct, okay, so this is only one way theorem, remember. So you have a graph in which minimum degree is n by 2, then it will be Hamiltonian graph, but the reverse direction is not correct. Okay, let's see this question. Does a path, okay, can a path be Hamiltonian and Euler path at the same time? Can a path be Hamiltonian and Euler at the same time? Is it possible? Is it possible? Can a path can be Hamiltonian and similarly can a circuit Hamiltonian and at the same time? So first you tell me about the answer for this one. First you tell me answer for this one. Tell me the answer for this one. Does a path can be Hamiltonian and Euler at the same time? So the answer is yes. The answer is yes. Like you take any Pn, you take A1, A2, A3, you take any Pn, this Pn you take. Now you can notice that if you take this Pn, this is Hamiltonian also, this is Euler also. You can notice this is Hamiltonian path also, this is Euler path also. Because you will visit every vertex exactly once, you will visit every edge exactly once. So this path is Hamiltonian also, Euler also. And what about this one? A circuit. A circuit, can it be Hamiltonian and Euler at the same time? A circuit. And the answer is again yes. You can take Cn. You can take Cn. This Cn you can take. Okay, like this Cn, A1, A2, A3, and so on, An. This Cn you can take. So for this Cn, you can notice that this is Hamiltonian cycle also, and this is Euler cycle also. Okay, so this Cn you can take. So this is very simple. So these we have seen. This is the summary. So tell me, in a Euler graph, Hamiltonian versus Euler graph. And when I talk about graph, then basically I am talking about circuit. So tell me, in this Euler, vertex repetition is allowed? Vertex repetition, is it allowed? Yes, it is allowed in Euler. Okay, in Hamiltonian, it is not allowed. Or tell me, age repetition? Age repetition is not allowed. In both of them, age repetition is not allowed. Because remember, if vertex is not repeating, then age is also not repeating. Okay, if vertex is not repeating, then age is also not repeating. And tell me, is it possible that you don't visit some vertex? Is it possible that you don't visit some vertex? Omitted means, is it possible you don't visit some vertex? No, this is not possible. But is it possible that you don't visit some edge? This is possible here. This is possible here. For example, you take this graph. Okay, like take this graph A, B, C, D. Take this graph. In this graph, what will be your Hamiltonian cycle? So this is actually Hamiltonian graph. And you can notice that this will work. Okay, go okay like this. Now you can notice that this edge is not visited. This edge is not visited. Okay, by Hamiltonian cycle. By Hamiltonian cycle, this is not visited. So this is fine. This is fine, no problem. Because the target of Hamiltonian is to visit every vertex exactly once. Okay. So is this clear to everyone? So these we have already seen. These things we have already seen. Next, this is your question. Can you solve it? This is GATE 2008 question. What will be the answer? Tell me one thing. What this question is saying? This question is saying that G is a simple graph. Okay. Some vertices are of odd degree. Add a vertex, make it adjacent to every odd degree vertex. Okay, so basically you have a graph. In this graph, there are many vertices. So let's assume many vertices you have. Like, okay, these are in this graph. Let's assume these are the even degree vertices. Okay, so let's assume these are the even degree vertices in this graph, like maybe B1, B2, and so on, Bm. Okay, let's assume these are the even degree vertices. And in this graph, these are the odd degree vertices. These are the odd degree vertices A1, A2, and so on, AP. Okay, AP. Now, what you are doing in this graph, this is a graph. In this graph, some vertices have odd degree. You are adding a vertex and you are making it adjacent to every odd degree vertex. You are adding this vertex, you are adding, and you are making it adjacent to every odd degree vertex. If I do like this, then what will happen? What will happen? These degree will be same, yes or no? These will not change. These will not change. These will be same. These will not change. But what will become this degree? But what will happen to this degree? Now what will happen to these degrees? These vertices. Now these vertices will become even degree. Okay, these vertices will become even degree. all of them, they will become even degree because they have odd degree. So odd plus 1. Okay, odd plus 1. So this is the idea. Okay, this is the idea that this is your graph and you are adding a new vertex B. You are adding a new vertex B. So you can notice that if you do this, then all these will become even. These will become even, like this will become even. This will become even. This will become even. This will become even. That is fine. But what about this degree? What about this degree? See, these are even degree, that is fine. These are even degree, that is fine, that is fine. But what about this degree? Why? Why this is even? Why this is even? Tell me. How can you guarantee that this is even? Please tell me, how can you guarantee that this is even? Because number of odd degree vertices is even. Very good, very good. Because number of odd degree vertices is always even. This number is always even. We know that. Okay, so this thing is important. Remember, every graph has even number of odd degree vertices. Even number of odd degree vertices. Every graph has even number of odd degree vertices. So this is the idea. So that is the reason. That is the reason I can say that this will be even. This also will be even. And what is the reason? The reason is this. The reason is this, that number of odd degree vertices will be even. Okay. So these were your previously odd degree vertices. These were your previously odd degree vertices. Now they will become even. So these are already even. They will become even because odd plus 1. Previously it was odd plus 1 even, odd plus 1 even. So they are even, they are even. But how can I say this is even? How can I say this is even? Because number of odd degree vertices is always even. So that is the reason. Finally every vertex has even degree. Finally every vertex has even degree. So your graph will be Euler graph. Okay. What about this? What about this question? Which of the following graph has Euler circuit? Which graph has Euler circuit? Which graph will have Euler circuit? Let's see. A k regular graph where k is even number. A k regular graph where k is even number. This is wrong. I told you. I have already told you this is wrong. This is wrong. Because connected is not given. Connected is not given. Counter example, you can take this. This is your counter example. This is the counter example. This option is not correct. Option A is not correct. Option B, not correct, because every vertex has complete graph on 90 vertices. So degree of every vertex is what? Degree of every vertex is 89. That is odd. That is odd. That is odd. Okay. Now tell me, what about option C? What about option C? What about option C? C is saying that the complement of C25, complement of C25, complement of C25. Okay, tell me one thing. In C25, what is the degree of every vertex? What is the degree of every vertex in C25? That is 2. That is 2. Tell me one more thing. If I give you a graph, okay, let's assume I give you a graph on n vertices. Let's assume this is the graph on n vertices. And let's assume degree of a vertex in this graph G. In this graph G, degree of a vertex is m. Then what will be degree of this vertex in G complement? In G complement, what will be degree of this same vertex? This vertex V has degree m here. It means this vertex is adjacent to m people. Then here the degree will be n minus m. Here the degree will be n minus 1 plus m. This is the maximum minus 1. Yes or no? Very simple. Because see, here the vertex is adjacent to total m people. Here the vertex is adjacent to total m people, and this is the maximum degree possible. So, okay, maximum this can be adjacent to n minus 1 people. It cannot be adjacent to itself, right? So this V, this cannot be adjacent to itself. So if this V has degree m here, then in G complement, this vertex, this same vertex will have degree n minus 1 plus m. Let's assume another vertex has degree P. Then what will be degree of this same vertex here? Another vertex, then what will be degree? That will be n minus 1 minus P. So very simple. Okay, so let's come back to this point. This is your C25. For all V. For all V, this will happen. What will happen to complement? What will happen to complement? What will happen to complement? So the degree of every vertex will be 25 minus 1 minus 2. 25 minus 1 minus 2. So, okay, for all V. So degree of every vertex is actually 22. Degree of every vertex, which is even. Is it enough? Can I say option C is answer? Can I say option C is answer? Can you say option C is answer? Every vertex has degree even. Every vertex has even degree. So can you say option C is answer? Tell me. Every vertex has even degree. So can I say option C is answer? Option A also has even degree. Option A also has even degree. You must prove that it should be connected also. Okay, so this is fine. Every vertex has even degree, but how to prove? Okay, but okay, is C25 complement connected? Is C25 complement connected? This is the question. Will it be connected? Is C25 complement connected? In general, tell me, Cn is connected for which values of n? Cn is connected for which values of n? Sorry, Cn complement. Cn complement is connected for which values of n? For which values of n? What about C3 complement? What about C3 complement? C3 complement is not connected. This is not connected. C3 complement is not connected. This is not connected. C4 complement is not connected. A, B, C, D. C4 complement will be like this. This is your C4 complement. This is also not connected. C4 complement is not connected. C4 complement is also not connected. Now, let's check C5. Let me check C5. Okay, let me check C5 complement. Let's see whether C5 complement is connected or not. Let me check. Okay, please notice this. Okay, please focus here. Please focus here. Very interesting, very cute proof is coming. Very simple proof is coming. Very simple proof. Okay, just focus here. Just focus here. C5 complement is connected, and very simple proof is coming. You have C5. In C5, you have these 5 vertices. Okay, like these 5 vertices, you have A1, A2, A3, A4, A5. Tell me one thing. Okay, now I will prove that this is connected. If I want to prove that this is connected, this graph is connected, then what should I do? If I want to prove, okay, to show, tell me what should I do? To show C5 complement is connected, what should I do? Okay, what we have to do? Show that for every 2 elements, for every A comma B, whatever 2 elements you take, for every vertices, there is a path between them. There is a path. Correct? Yes, very good. Kushal, very good. There should exist a path. If you want to prove connected, then what you have to do? If you want to prove this graph is connected, to show this graph is connected, this is your graph, C5 complement, this is connected, then you have to prove that for every two element there is a path. Now, in this C5 complement, let's take two elements. In this C5 complement, this is your C5 complement, this is your graph. Your graph is C5 complement. In this, let's take two vertices. Okay, let's take A comma B. Let's take two vertices A comma B belonging to C5 complement. Tell me, do they belong to C5 also? Do they belong to C5 also? A comma B. Do they belong to C5 also? Tell me. A comma B belong to C5 complement. Do they belong to C5 also? Tell me. When you do complement, vertices are same. Yes or no? Vertices don't change. Agree or not? So the vertices will not change. This is your graph. This is your graph. Let's assume that A comma B belong to C complement. Let's assume. Then automatically means that they also belong to C5, because vertices will not change. You know the definition of complement. The definition of complement says that vertices will not change. You know the definition of complement. What is the definition of complement? If you have a graph G, which is V comma E, then G complement will have the same vertices. Vertices will be same. Edges will complement. Vertices will be same, but edges will complement. Vertices will be same, edges will complement. So you can notice, let's assume that you have two vertices, you are taking two vertices A comma B. Now, one thing you notice, there are two cases. What are the two cases possible? Please tell me, what are the two cases possible? Case one, A comma B A comma B adjacent in C5. Either they are adjacent in C5, yes or no? Either they are adjacent in C5 or they are not adjacent in C5. A comma B are not adjacent in C5 or they are adjacent in C5. If they are not adjacent in C5, then what will happen? Only two cases are possible. Either they are adjacent or they are not adjacent. If they are not adjacent in C5, then what will happen in C complement? Then in C5 complement, what will happen? They will be adjacent. So there is a path. So there is a edge, and there is a edge means they are path, means they are connected. It means they are connected. Okay. In C5, if they are adjacent in C5, if they are adjacent, then in C5 complement, if they are not adjacent in C5, then in C5 complement, they will be connected. Now let's see this one. If they are adjacent in C5, then what will happen? Like they are adjacent in C5, they are adjacent in C5. So they are adjacent, like, okay, this is your A, this is your B. They are adjacent in C5. Then what will happen? Then what will happen? Now you can notice one thing. This vertex, they are not adjacent to this, yes or no? This vertex, they are not adjacent to this vertex. Agree? Both of them are not. Okay, so there exists a vertex. This vertex V. Look at this vertex V. This is your vertex A. Okay, notice that this is your vertex A. This is your vertex B. Now look at this vertex. So you can notice that A comma B are adjacent in C5. Then there exists a vertex. There exists a vertex which is not adjacent to any of them. Which is not adjacent to any of them. To any of them. Yes or no? This will happen because they are adjacent. A1, A2, A comma B, they are adjacent. This A comma B, they are adjacent. Then this vertex, you cannot, they are not adjacent. There exists a vertex. This vertex, this vertex is not adjacent to any of them. This vertex is not adjacent to any of them. So there exists a vertex which is not adjacent to any of them. Then what will happen in C5 complement? Then next page. Then what will happen? Okay, so this case one we are discussing. This case one we are discussing that you have A comma B. Okay, they are not adjacent. A comma B, sorry, A comma B are adjacent in C5. They are adjacent in C5. Then what will happen? Then there exists a vertex which is not adjacent to any of them, which is not adjacent to A comma B in C5. Then what will happen in C5 complement? Tell me. Then in C5 complement, they both will be adjacent to V. Yes or no? Very simple. They both will be adjacent to V. They both will be adjacent to V. So you have a path. So this is your AB path. So this is your proof. Did you understand this proof? Please tell me. Very simple proof. So only two cases are possible. Case one, case two. Only two cases are possible. In both the cases, we have path between vertices. In both the cases, A comma B are connected. In both the cases, A comma B are connected. A comma B have path between them in both the cases. And hence prove. This is okay. Is this clear? Hence prove. In C3, this is not there. Nikhil, in C3, this is not there. This is not there. See, in C3, this is not there. Here you notice this A comma B are adjacent. First, you please see this C5. This is your C5. You tell me in this C5, A comma B are adjacent. There exists a vertex. There exists a vertex which is not adjacent to any of them. Nikhil, there exists a vertex which is not adjacent to any of them. But in C3, this is not the situation. In C3, this is not the situation. In C3, what happens? In C3, everyone is adjacent to everyone. So the C3 complement will be what? So the C3 complement will be this. Everyone is adjacent to everyone. This is the problem. Everyone is adjacent to everyone. Also in C4, this V does not exist. In C4, you can notice there is no vertex, like they are adjacent. These two are adjacent, but there is no V, there is no vertex which is not adjacent to any of them. Can you notice? Like this vertex is adjacent to A, this vertex is adjacent to B. But in C5 and more than C5, what will happen? In C5 and more than C5, in C5 and more than C5, what will happen? This will happen. In C5 and more than C5, this will happen that if they are adjacent, then there will exist a vertex. There will exist a vertex which is not adjacent to this, which is not adjacent to this. This simple thing, this is the simple observation. If you take Cn, where n is greater than equal to 5, then this simple observation you can make that if A comma B are adjacent, then there exists a vertex. There exists a vertex V which is not adjacent. Then what will happen to C5 complement, like Cn complement? What will happen in Cn complement? In Cn complement, what will happen? This will happen. A, B, this will happen. So you can notice there is a path, and this is your path. To how many people is this clear? Let me know. Very simple proof, very simple. Very simple proof. Did you understand? So in C3, in C4, it will not happen. Okay, but in C5, this will happen. In C5 and also n greater than equal to 5, whatever you take, this will happen. That there will exist, this is important, there exists a vertex which is not adjacent to any of them. This will happen. Like for example, in C5, you can notice A, B, C, D, E. whatever two vertices you take, for example, they are adjacent, for them this will work as V, yes or no? For them this will work as V. In C6, A, B, C, D, E, F. In C6, like they are adjacent, for them this will work as V. Okay, so whatever Cn you take, whatever Cn you take n greater than equal to 5, so if you take consecutive vertices, then for them there exists a vertex which is not adjacent to any of them. So this is the cute thing that is happening. So finally what I can say, this is the final conclusion I can say. Is C5 complement connected? The answer is yes. C5 complement connected? Answer is yes. And Cn is connected for which values of n? N greater than equal to 5. N greater than equal to 5. So that is the reason option C is the correct answer. This is your GATE exam. Can you notice? Just think about it. If this question is MSQ, then majority of the students will make it wrong. Majority of the students will do this also, this also. Yes or no? Like many students will answer option A. Let me tell you, many students, they will answer option A. And if this is MSQ question, then students will answer both of them. But the answer is, what is correct? Only option C is correct. This type of questions, okay, this type of questions is all you need to solve. And let me tell you one more thing. Okay, if you watch on any website, okay, you can ask your friends who are not in the Go classes. You can ask them, what is the answer for this question? You know what they will say? They will say that here every vertex has degree 22, so answer is this. This is what they will say. They will say this, yes, degree is 22, so this is the answer. They will not worry about connected. They do not worry about connected. But just think about it. Here also you have even degree vertices. Here also you have even degree vertices, but may not be connected. May not be connected. May not be connected. And here you have even degree vertices. Here also you have even degree vertices, but this is connected also. Many people, they don't think about connected. And one thing is surprising to me, actually, almost 2 years ago, this happened. So before this Go classes, before we started Go classes, so this question, one student solved it. I asked him, so how did he solve? He told me this same logic. He told me that, sir, here every vertex has degree 22. So this is Euler. I told him that here also every vertex has degree even. Then he told me, sir, this may not be connected. Then I asked him, is this connected? And he did not have the answer. Okay, so whatever question you solve, solve with correct understanding. Okay, let's move on. What about this question? Please tell me the answer. This is GATE 2006. If all the age weights in an undirected graph are positive, all the age weights are positive, then any subset of edges that connects all the vertices has minimum total weight. What is that? So actually, if all the edge weights are positive, any subset of edges that connects all the vertices and you must connect all the vertices and has minimum total weight, then it should be, what it should be, A or D? Option A or D. Why not? Okay, so this will be actually minimum spanning tree. Don't worry about it. This you will study. This question you will solve in the algorithm subject. Actually, this is your algorithm subject question. This is algorithm subject question. You will study. There is something called MST, minimum spanning tree. So there you will study. But tell me why this option is not correct. Why this is not correct? Why this one is not correct? Yes, because of cycle. Because of this, it is not correct. Because of cycle. Just think about it. Like, let me give you a graph. Let me give you this graph A, B, C. This edge weight is 2, this edge weight is 1, this edge weight is 3. Okay, let's assume this is your graph. Now for this graph, you can notice that subset of edges which connect all the vertices. So you can notice, and with minimum weight. So what is that? Which connect all the vertices. Subset of edges which connect all the vertices with minimum weight. So this you will get. And this is a tree. This is not Hamiltonian cycle. Okay. This is a tree. This is not Hamiltonian cycle. So that is the reason answer will be option D. This you will study in the algorithm subject. Let's move on. Okay. This is another question. This is GATE 1991 question. And this is saying that show that all the vertices in undirected finite graph cannot have distinct degrees if graph has at least 2 vertices. Means this is saying that if you have a graph V comma G, if you have a graph such that number of vertices is greater than equal to 2, then at least 2 vertices will have same degree. At least two vertices will have same degree. At least 2 vertices will have same degree. Okay, like you cannot have distinct degree for all of them. You cannot have distinct degree. Okay, all of them, they cannot have distinct degree. At least 2 of them will have same degree. Tell me one thing. When you see this word, at least 2 vertices have same degree. When you see this, then what comes to your mind? At least 2 people go to the same degree. At least 2 people go to the same degree. What comes to your mind? At least 2 people go to the same degree. At least 2 pigeons go to the same hole. At least 2 pigeons go to the same hole. What comes to your mind? Tell me. At least 2 pigeons go to the same hole. Pigeonhole. Pigeonhole principle. At least 2 people. Okay, pigeons. These are your pigeons. At least 2 vertices. Vertices are your pigeons. These are your pigeons. And this degree, these are your holes. Pigeonhole principle. Is this clear? So you can very simply, you can prove it using pigeonhole principle. Like there are 2 cases possible. See, let's see the proof. And this is a very simple proof. Very cute proof. Okay, there are 2 cases possible. Either case 1. What is case 1? Your graph is disconnected or connected. Case 1 is your graph is connected. This is case 1. Okay, so this is case 1. See, this is the statement. Karthik, this is the statement that any graph, you take any graph with at least 2 vertices. If you take any graph with at least 2 vertices, then at least 2 vertices will have same degree. At least 2 vertices will have same degree. You cannot have distinct degree for all the vertices. Like all vertices, they cannot have distinct degree. At least 2 vertices must have same degree. So how to prove it? There are 2 cases. Either the, okay, this is case 1 and case 2. Case 2 is disconnected. What is case 2? Case 2 is disconnected. Only 2 cases are there. So tell me, in this case, what will happen? In this case, if your graph is connected, then what is the possible degree? Tell me, what is the possible degree? How many degrees are possible? Possible degrees, please tell me. What are the possible degrees? If your graph is connected, then what are the possible degrees? Number of vertices is greater than equal to 2. Then what are the possible degrees? Because your graph is connected, can you have 0 degree vertex? Can you have 0 degree vertex? Because you have connected graph, so you cannot have 0 degree vertex. So these are the possible degrees. Only these are the possible degrees. And how many vertices you have? Tell me how many vertices you have. How many vertices? Total n vertices you have. So you have n vertices, and these are the possible degrees. These are the possible degrees. Can I guarantee at least two vertices will have same degree? These are the possible degrees. Can I guarantee at least two vertices will have same degree? Yes, these are the pigeons. These are the pigeons, and these are the holes. You can notice that number of holes is less than number of pigeons. So we can guarantee. You can very easily see, like these are your vertices. Your vertices are A1, A2, A3, AN. Let's try to see that they have different degree. Let's try to give different degree. To this, let's give degree this. To this, you give degree this. To this, you give degree this. If you do like this, then what will happen? If you do like this will have degree n-1. Now what this degree this will have? What degree this will have? One of them. So I can guarantee that at least two vertices will have same degree. So okay, for connected graph, what can I say? So for connected graph, okay, with a number of vertices at least two vertices have same degree. Is this clear to everyone? At least two vertices have same degree. At least two vertices must share a degree. They must share a degree. At least two vertices, they must share a degree. And what happens if you are disconnected? If your graph is disconnected, then what are the possible degrees? What are the possible degrees if your graph is disconnected? Possible degrees. Your graph is disconnected. Then the possible degrees is 0 to. Is it possible degree? Tell me, is it possible degree? Is it possible? Is it possible? This is not possible. This is not possible. This is not possible because your graph is disconnected. If you have this, then your graph will be connected. If you have a vertex with degree n-1, then your graph will be connected. So in disconnected graph, no vertex has degree, no vertex with the degree n-1. No vertex has degree n-1 if your graph is disconnected. Okay, so again, this is your possible degrees. And what is the number of vertices? Number of vertices is n. So these are your pigeons. These are your pigeons. And how many holes you have? These are the holes. How many? n-1. So number of pigeons are n. Total n pigeons you have. n-1 holes are there. So then in this situation, again, I can say that for disconnected graph also what will happen? I can say that for disconnected graph also what will happen? If your graph is disconnected, then also at least two vertices will have same degree. So every graph. So finally I can say this is the final note. Every graph G where number of vertices is at least two. Every graph with number of vertices at least two has at least two vertices of same degree. Okay, is this clear? Let me know. All these concepts, are they clear? So this is enough for today. In the next class, we will study this graph realization problem, this Hubble-Hakimi and all these things. So this Hubble-Hakimi will come here. This we will study in the next class. If anyone has any doubt, you can ask. Please let me know if you have any doubt. How many lectures are pending? I think 1, 2. 2 lectures. Saurabh, tomorrow and day after tomorrow. Only 2 lectures. and graph theory is over. So if anyone has any doubt, please let me know. Any doubt, anyone? Okay, thank you. See you tomorrow. Hello, Nikhil.
Sir, am I audible? Good morning.
Yes, yes, good morning.
Sir, I have a doubt in the property that you told us that omitted node allowed in the Euler circuit or not.
Yes.
Sir, I have a like graph like C3 plus isolated vertex.
Yes, I knew you will ask that.
But sir, that the vertex is now omitted and then we have a Euler circuit there.
So actually, there are some authors who allow isolated vertices in Euler, but there are some authors who do not allow it. See, actually, if you notice, like I have this, like Grimaldi does not allow it.
Okay.
So here you can notice. So actually, what, for example, here this is Grimaldi, and Grimaldi does not allow it. You can notice this is from Grimaldi actually.
Okay.
So you can notice Grimaldi says that you should not have any isolated vertices. But what you are saying, that is fine. There are some authors who allow this isolated vertices. And let me tell you one thing. See, these GATE exam questions, they will be created by professors, IIT, IISc professors. So these professors are not like coaching teachers. Okay, yes, these are not coaching teachers. They know everything. They have written research paper. Some of these concepts they have proved. Some of these concepts they have come up with. Okay, so you can notice they have written books. So basically, they know everything. They know how to create a question. In the GATE exam, there is no question of Euler path, because they know that this is ambiguous. If they give you any question of Euler path, then they will have to define it. Okay, so basically whatever question comes in the GATE exam, you can notice one thing, that will be unambiguous. Similarly, like you are saying that this isolated vertex, some authors they allow isolated vertices, I know, but some authors do not allow it. Okay, so what I am taking, everything that I am teaching you, that is based on NPTEL lectures and also ISC lectures.
Yes,
because
sir.
the reason is ultimately these professors will be creating the questions.
Yes, sir.
Okay?
Yes, sir.
So you can follow just the lectures. Just follow the lectures. You don't have to worry about other things. Yeah.
So in case like these sort of discrepancies are there, like they will mention in the question itself, right?
There is no ambiguous question. You can solve like 40 years question you can solve. In graph theory, there are many, you can notice one thing. In graph theory, there are many, I can say, ambiguities, right? Yes or no?
Yes, sir.
But still, in the last 40 years, there is no ambiguous question.
Ambiguous
So
question.
the GATE professors, they know everything.
Okay.
So you don't have to worry about it. Never worry about ambiguous concepts. Never. Just follow one thing. Follow one standard resource.
Okay, sir. मैं समझ गया. Thank you.
Any other doubt?
No, sir. Sir, all clear.
Okay.
Thank you, sir.
Any other doubt, anyone? Okay. Thank you. See you tomorrow.